Since that's when you turn. I have a lightning hand too. I just don't ever wear it. Oh, just the blues. You've been seeing all these crazy memes, man. Like they showed one with Stamkos, like might get swept. I don't know. He's feeling cute. Might get swept. I don't know. IDK bullshit. No, it's a disease right now on the web. Yeah. Oh, they're all out? Like out?
He kept like the big stars out. So that way they wouldn't know. So he had like 2.5 minutes of playtime.
Wasn't it a close game?
Yeah, and then they pulled fast.
They get open net goal.
And they're
They go to the solidworks. Are we just gonna do like a basic bar? Oh yeah. We're doing the tetrahedron, aren't we?
Yeah, cool. Dimensions and everything apart. Those are together. And not running the FEA on that.
Kind of excited about learning this.
All right. So today we're going to do local analysis. Finding element stuff. And basically demo that is broken down to some extent in the PDF titled solidworks demos. PDF. Look at. We're going to do a very simple structure. Basically, very simple piece of steel. We're going to actually fix one end. We don't have to, but I want to show you how to fix it. And then we're just going to do the more analysis. All right. So hopefully you have your laptop with SolidWorks so that whatever here. But any questions you have to ask, all probably are more efficient at using SolidWorks from a modeling, solid modeling point of view than I am. I just don't. So there's probably quicker ways to do something as far as bringing geometry. When I really push that much for this. We're going to shape, so we'll do pre-processing, the solution, and the post-processing. Like we talked about it last Thursday. And then we go over what you need to do for project 2. All right. Project 1 has been graded and will be available. That's how the grade was posted last night. Today. Will be available in the ME office for your pickup at noon. I can do it. Any questions that you have on that, I'm happy to answer. Any questions that you have on project 2? All right. At this point, it's Tuesday. Thursday will be a review. Today will be the third exam, and then we'll finish. No final in here. And a week from Thursday is actually the so I can't touch that. So as far as the 2 days, like meaning I can't touch it. I can't make anything do. I can't expect anything out of you next Thursday or Friday. The due date, project 2 will be a week today. All right. Maybe something to read today.
Just gotta yell at him.
Can you hear me now?
Wow.
All right. So, you hear anything that I said?
At the beginning of the
Let's start. Today we're going to talk about mobile analysis using finance software. Software using solidworks simulation. And explain why we use it. It's the only software that 99% of the time we have license for. All right, and systems and other packages we have, which is a little better with respect to our own selection. Honestly, we never had a license, but I did it for the class. So we are using solidworks simulation to demonstrate mobile analysis for a very simple structure. And basically, we have a PDF, like a SolidWorks demo, that PDF that's uploaded to standards. That is one of this course. I'm going to basically just be following along the first page. And then I do want to show you how you can understand me doing this for a time of analysis. All right. So we'll do that. And then I want to go over project 2. All right, which is again, basically do the same kind of analysis that we're doing right here for those two structures that are mobile. All right. And the due date that will be the beginning of class. Today, we're going to do demos. Thursday, we're going to have a review, some regular questions. I'll bring up the test from last semester. I've written the test. Honestly, I think it's easy, but apparently I know you but what is test is different. But don't count on it. By easy, I mean, you have to show up, you have to participate, you have to do all those things, and you have to understand what's going on. Right? So if you don't know the class, okay, so that's the rundown. Today, mobile analysis with FEA, my own software, and then Thursday reviews, you make your exam. Beginning of class, and do a day, project 2 is good. Everybody heard that, right? I don't take great projects. I may take them and put them in a folder, but I'm just, unless you got a real good excuse, but I got at least one. I don't take great projects. Okay, and now projects will work a whole lot. It's really meant good time for you. So even if you do it, you don't get credit for it. All right. And any questions that you have, please ask. Please ask. Now's the time to ask. All right. So I've opened up SolidWorks, and the first thing that I want to do is I want to check and make sure that we have the proper add. I'm going to put my glasses on so you can see. So tools, add-ins, under here, I'll go add features. And if you scroll down a little bit, you'll see SolidWorks simulation. There's a check mark on both sides there, so it should be active and it should come up on startup. So SolidWorks simulation started here. If yours doesn't have that check, then you're not going to be able to solve it. All those features will not be available. All right, so that's the first step, and that's the very first thing. Next up, I'm going to create a new file. All right, it's just a part. You can do assemblies and things, but we're just going to do a part. notes are for part in SI units, millimeters. So that's what I'm going to try to use when we come down here and change this. Using millimeters. I think the drawings you have probably are in English units, correct? Not really a big deal with SolidWorks because we have historically, perhaps historically, when you had to put your own material properties in, you English units have to be very careful and understand how the folks that wrote the program are using units. Because we use pounds per cubic square inch or whatever, instead of slugs per cubic square inch, slug is, then you run into problems. And of course, you can always stop the problems if you've got data. And so anyway, we're after messing with that. I tend to always prefer SI units. So SolidWorks doesn't have material libraries there. It knows how to find properly. All right, so we got a new part. And so first thing you look up here at the top of the main tabs, you're very familiar with these. You've got the sketch, evaluate. Those are the two that we're going to use initially. Create our very simple solid model. And then the simulation tab is the one that should be going to FEA. All right, so it's sketch tab, and I'm going to grab one of the planes for drawing purposes. Grab a right plane, and then I'm going to go and for cross section of my very simple structure, corner rectangle. So my cross section has a base of 50, a width of 50 millimeters, and a height of 10. Try to draw that out close. And we're going to fix it. So if you're following along, we'll have the same numbers. It's not really that important. There's basically got base and width, that's about 15, 10. Like that, so we're good to go. And now the next step is for the fusion. We want to extrude this. We're going to extrude that. And we're going to make the length of this structure 200 millimeters. Almost 10 there, you can see. All right, so there it is. So what have we just done? We've done for step one of our pre-processing. We created a solid model, find the geometry. Still haven't specified the material or material properties, so we're going to do that next. And the material that I'm going with is plain carbon steel, and I'm going to right click on the material here, and you can of course hit edit material. You see plain carbon steel is number one here. Material. All right. So scroll down through here. There's my plain carbon steel, and then you go into plastics. What you're going to do is because you've got your parts that you're doing are acrylic. So here's the one part. We'll get to separate. Those are your letters you guys have construction. One of them is acrylic for the drawing, and the other one is PVC. All right, so the material specified on the drawings. Go with that. But they're over here. I've got plain carbon steel. So that's what we go with. And we select that. Gives us a bunch of information that's used, but really the only thing that's going to be used for our creation, application of the creation of the passive system. our elasticity, the reinforcement ratio, and investment. We're not going to push this thing really hard. Linear analysis, no damping. We want to introduce damping as proportional damping to mold damping, so we introduce it after you do the mold analysis. All this additional information going on for the good strength and so forth. We're going to be pushing this thing beyond its elastic limit or subjecting it to temperature gradients that we work at this time. All right, so apply, and we'll see when we do that. Now specifies material. All right, so we've done the first two steps of our pre-processing. We define the geometry, and we've also defined the material. More importantly, material properties. All right. What are the other steps of pre-processing? Boundary conditions. All right. Yeah, defining elements. So that's the fourth step. So we mesh, and that's part of it. And we define the boundary condition. Now, with solidworks, way it's set up, you can do it in either order. A long time ago, most of the software packages had to do your mesh, private elements, separate steps, and then mesh, separate step, manually or automatically. And then specify your boundary condition. SolidWorks is an algorithm that automatically figure out based on what area or surface, I should say, you're applying the boundary conditions to. You can figure out once you measure it what node to apply. Because your boundary conditions are usually going to apply to the node. The node, the default node displacement to the node. That's the next big saving step. The place that I introduced both the boundary conditions and the mesh is in under the simulation. So at this point, I'm going to go ahead and click on simulation, and you see at the top, make it pretty simple. Study as our choice. So we'll pick a new study, and this is where we have some options. So we can do static analysis, thermal analysis. Now, this is one area where SolidWorks, I think, could really aid things. I don't know why anybody that really refers to mold analysis. So, this is what the study we want to do. We want to basically what it's going to do. It's going to do the first 4 steps, 5 steps of the 8-step procedure. It's going to do more than that. It's going to help us form the next. All right. In addition, what we're going to do later, we have a little time, we're going to come down to linear dynamic. And under there, we can do time domain analysis. So we actually want to look at how structure behaves through an impact or the shape or touch or something like that. Do that. That's when we introduce either mold damping or proportional prior to that. Mode shape and measure frequency on the other the same without any damping. Right? And of course, the software is not going to let us do only damping that leads to proportional. Only damping that leads to normal loads. All right, so we'll select frequency here, and you can give it whatever name you want. Frequency 1 is fine with me. And so there's only one part, so that's the part fixed thrown underneath the frequency 1 study. And so at this point, what we want to do is I'm going to go ahead and just define my boundary conditions first, even though it's opposite of what I used to do, because it's just next to the line here. We've got our part on, there's really no connections, once that was one part. And so now we're going to introduce our pictures. All right, so I got that. And what I want to do is just grab this thing here. And right click on fixtures, I'm going to fix that left face. This right here. All right. Then you see you got different options you can do. Slider, roller, hinge, elastic support if you wanted to do that. I'm going to fix it. If I had done a mold test on this in class on a piece of foam, what would I use for boundary conditions? None. We'd be done. There would be no boundary conditions, right? What effect is that going to have on your results? You're going to have 6 rigid body nodes, which means what? Your first 6 edge preferences are going to be very, very close to 0. Why aren't you going to be exactly 0? I don't know. You're a player. All right. So I already got one email. What about the boundary conditions? Is this the right video? Oh. No boundary conditions. Good question to ask in class. So let me get the question. Okay, that's good. I appreciate you doing it. Yeah, no boundary conditions. The first 6 nodes you're going to do. I don't want to show you boundary conditions because I want to show you how to do it if you want to. All right. Yes. What? That'd be an easy one, but I can obviously, I don't know if I asked you. I already wrote your test. Possible. Everything's possible. All right, so we're going to just do a fixed geometry. Now it's looking for face, and you can, of course, at this point, you can still specify something other than fixed. And of course, you see, as soon as I get anywhere near that face, it gives me these lovely little green constraint codes. All right, and the typing constraint, I'm not really going to show you all that, but I'll just say, talk about it. We can define how it's fixed. In other words, you can fix it so that it's only constrained in a plane, translationally or rotationally. If you just grab the default mechanic, it fixes it with respect to everything. So it's fixed in all 3 directions, and it's fixed in all 3 angular directions. That's what we're going to do. Fixed. Select that, not go there. So we selected that face, it's called phase 1. Fine with me. We'll pick that. And now we've done the 3rd step, which is to find our boundary conditions. Right? Boundary conditions for yours, you're not going to fix anything. The boundary conditions there will be free. Right? So I don't want to say you don't have boundary conditions. You do. It's just nothing fixed. All right. The last step is the mesh step. So we're going to right click on mesh. You got some options here. We're just going to use the mesh tool, which is called create mesh. All right. It's called create mesh, and that's fine with me. We need to select. I guess we probably wanted to select that first. Okay, so I think it's there. So as soon as everybody follows, we need to back up. So mesh, create mesh, and now we've got this sheet auto mesh. It says mesh, and that's fine. You see the very first thing you think is the mesh density. You can make a really coarse mesh or a really fine mesh. Or down the middle of the line. Right? This computer that I have is not exactly what I call high speed. It's probably nothing to do with the browser. It's everything to do with that work. But I'm just going to leave it in the middle to see what happens. All right. If I was using a really slow machine, and I may be, I'd probably move that down in course. That's going to decrease the number of nodes and elements of those and speed up, reduce everything size of my matrices, the amount of computational power we need to solve it. All right, I'm just going to go with that. And you can set mesh parameters if you want, like, edge length, and things like that. Looking at there. So if you wanted to pick the draft quality elements, they call it draft quality mesh. Basically, going to be the draft elements. We're just using the elements of SolidWorks used for solid models is pyramid shape. And they have a draft model, draft element, which basically only defines nodes and points. And then they have a second order model, which defines nodes and points and at the midpoint of the edges. That's the one that's used by default. I'm finding the default. So we're just going to hit check. That should mesh it. All right, now if you look at this mesh, then I guess we could reset this so we're looking at it a little bit. Okay. A little dark, but if you look, listen to this edge right here. You see 1, 2, 3. So there's 3 elements on the shortest dimension. That's pretty good for vibration. If you're just stress analysis, me and what stress shadings over here, they probably not good enough. For our purposes, it's fine. Even if you break it down. So we've got a lot of elements, a lot of nodes, and if we want to determine how many we have, honestly, I need to try to remember how to do that. You put details, so I want to thank you. I thought you guys were better faster at this than I am. So it tells us study the mesh type, the solid mesh is going to use the attribute elements. Which is standard mesh feature. Some other features here you can use. We didn't use any. Element size 4.6, like the average element edge length. How much is pretty for that, I guess. Mesh quality. So here we go. Total number of elements. Basically 8,300 elements. Big step from what we did in class, right? When we're doing things by hand, why not? After they can expand and add, no problem. Each one of those little elements has what? Stiffness and mass matrix, right? And nodes associated with it. And all the software is going to do is it's going to basically take all of those and expand them and add them and get that will define mass. Corresponding number of nodes is 13,500, 2.5, 4,000. You might expect it to be a little bit higher, considering how many elements we have. The reason why it seems kind of low is because there's a lot of sharing. There's a lot of sharing. All right. Okay, so let me go to box. There we go. All right. I don't know how you can see this. I'm going to come back to it, but I just want to point out project 2. This is the project sheet. One of the things I want to make sure you include is mesh images of the components. That's the first type. You've got 2 components, right? Mesh image of the component, that's what it shows right here. This shows the mesh image of the component. It shows a lot of useful information. This might not be the best view. You can't really see it. I might have to go over it a little bit. Bring it around a little bit, try to see that. But it shows what? It shows the geometry. It actually shows, it doesn't show that it has to be an element. Not clear if we're using a graph or not, but I can shake it before. By default it is, and then it shows that the front face is fixed. Right? So this is one of the parts that we tested, or somebody's asking me to show the mesh image of my structure. This is what I would show. And how would I do that? I would come up to save. JPEG. I don't use JPEG either, but there's other ones that okay, let's take the JPEG. Some sort of image. Part 1, call it whatever you want. Structure, page, whatever you want to call it. That's what it is. Save that somewhere on your computer and what it'll be is basically an image. All right, now if it does pull up this stuff and this stuff, you can always crop it so you just have the mesh. All right, and add your eligible. Everybody understands that? What's this again? Okay, go ahead. Yeah, so I'm having a hard time seeing this. This might just be the lighting here. I'm having a hard time kind of seeing this edge over here. So, you know, that's fine. Of the best view that you can see the geometry. There's no constraints on your images, so that doesn't matter. It's just the best image to show. All right. Good question. Thank you for asking. So what have we done? Pre-processing. All right. And some folks, you know, by the time they get to this point, now it's not working with 30 especially what's but it may go pretty quick. So the next step is to do the solution. We're going to go to frequency, right click on that. We don't want to just go to run yet because we haven't really defined like the range that we want to study. And this can go to pretty high frequencies. So what we're going to do is we're going to go to properties. All right, now if you look at the properties, the default, there's some options. The default option is number of frequencies. It's set to 5. You can instead, there's some different things you can do. I mean, you can rerun this. You have it on your computer, hopefully, or at least in the lab or something. What I would recommend, honestly, is an upper bound frequency for you, because the measurements, none of them exceed 2,000, right? One structure would be below that. Okay. So just pick, I would go like maybe a couple hundred over the max, the maximum frequency that you extract. Just go out a little bit. In this case, this is a pretty stout little piece of steel. It's fixed, and so I don't honestly remember frequency range of 5. I'm not going to cut it. I want to be able to show you the longitudinal modes and then modes and talk about those ones that we're going to put. Now you may, if you pick this here, set your upper frequency limit to 2,000 hertz. You may get several dozen modes, right? And from that, you want to find the 2 or 3 that are closest to the ones that you measure. Those are the ones you want to focus on. All right, that makes sense? Any questions at all at this point? So let me ask you, why do you think we only measured 2 or 3, and yet this software is going to compute maybe a dozen or 2? Yes. Yeah, because we're only measuring in one direction, one part of the other. But yeah, I mean, we didn't really move the sensor. We only had one sensor. Just did a quick test, and I'm going to show you about software. If we really had hours spent at it, and wasn't start with people, I could probably move around and got to watch it. But yeah, depending on your orientation. So you want to just try to zoom in on, focus on one step. So we're going to pick a point here, and so we'll extract point. All right, and at this point, we're good to go. Ready? Very fast. All right, so the very first thing you notice here that it basically gave us results folder populated it with point modes. Those are basically going to show us the modes. Before we look at that, I'm going to right click on results. If you look under there for a minute, you'll see list resident frequencies. Another way of saying that. Here's our 20 measures. So that's curious. Maybe. All right. So the nice thing about SolidWorks is that it gives you the natural frequency in different units. Okay, the error, the possible error that students make, or folks that are new to this make, is that most of the measurements we use hertz when we take measurements. And I'm not sure why that is. Folks that design and analyzers just pretty much make it that way. You can change it, I guess, if you want to default to this hertz. In calculations, radians per second is common because otherwise you're carrying a 2 pi everywhere in all your equations. All right. So here they did a nice job because they give us some natural frequencies. The center column with hertz, the left column with radians per second. Period. I don't know why we're doing that, but our measurements are taken in hertz. Right. So this is probably the column. And down through there, and if you see when that matches up, then just make a note of what node it is, or mode, what mode it is. All right. You can see this is a stout little piece of steel. The first natural frequency is over just a little over 200. Next from there is 1,000. It goes up. This is a really within the first 4 modes occur under 2,000. All right, any questions? I don't need to see the whole table, right? Yeah, go ahead. What? A little louder.
How are you going to 20 amplitudes and results?
How? Yeah. That's what this one will do next. I'll show you. All right. So let me, before we do that, I'll get this contact up. All right, so number 2, that's kind of small. Number 2, table of modal testing measured natural frequencies in project 1, and corresponding point element method computed natural frequency. By corresponding, I mean what? Ones that match up the closest. All right, so that's the table with a percent difference calculation. Right? How do you guys calculate percent difference? I'll tell you how I do it. As long as it's close to it, it's fine. I take what I consider to be one known quantity. I take no less known quantity. Subtract the known quantity divided by the known quantity. So I would take the actual computed, subtract the measured, divided by the measured. Let me do it like that. I know that if you don't mind, I'm not going to nitpick that. Define what you're doing percent difference. The way that I do it and always do it, and always done it exactly the way I would take, in this case, the measure to me is the reality. My measurements are good. And so the calculations are the ones that are questioned. Calculated minus measured, divided by measured times 100. All right. And as long as we're here, step 3 is images of the relevant mode shapes. So you're going to extract that three natural frequencies from one structure, 2 natural frequencies from the other structure, correct? So now at this point, step 3, we're going to get images of 3 mode shapes from one structure, 2 mode shapes from the other. I mean, I don't know if you guys in the lab or something, if they're really held down taking extra values. If you want to define it different than what I just described, just define it. Yeah. But I never do. I always just want to be able to see the function. All right. So looks like the first node was up here. You look up here. 211 says mode shape natural frequency. And so what I want to do now is kind of hard to see anything. This is some nice color scale, which obviously because the scale, all it does is give us a relative reflection. And I'd rather look at it. So what I want to do is just kind of see if I can figure out what this is doing. I know it's I want to kind of know. What I want to do is I want to animate it. Right click on that first mode and track with you. Hit animate. Right? That's a bending mode. I see. That's what I would call, looking at my reference step where it's down here, X, Y, Z. That would be a bending mode in the X, Y plane. How many heard what I said? Understood it. How many understood it? That's a bending mode in the X, Y plane. You see that? There's a front view for the XY plane. See it? XY plane right here. That is everything's happening with the XY plane. We call that engineering. You study the portions, 2 portions. All right. Is that 211 hertz? No. Slow it way down so we can see it. Is it really going to vibrate that much? No. Plastic will be right, you see vibrating, so you can see it showing us the relative. All right, so we'll stop that. That's not a bad image right there. I kind of like to include X, Y. I mean, they have to kind of move that up there so you don't have to waste so much paper. My PA says you guys kind of waste so many wasted paper on project 1. Don't waste paper. But, you can always just draw X, Y by hand as well. And again, if you want to say this is an image, go in, save this as a tip for a JPEG. We don't need this scale. I can see the scale just looking at it. Nothing's moving here, it's fixed, and it's moving here. And even if it wasn't fixed, you can see a relative displacement. Now, one of the things that can happen is sometimes, for some weird reason, this relative scale can be exaggerated. This isn't bad. Don't get me wrong. This is exaggerated how much it's going to go 200 times a second. You'd be able to feel it, but you most likely wouldn't see it. All right? But from a point of view of showing what's happening, saying, hey, that's a first one bending the XY plane, that's a reasonable scale. And that's a very good view, by the way. See that everything. If we go to settings, I think it's settings or edit definition. Yeah, it's that's the you go to your mode, go to edit definition, and now just kind of pull that out a little bit. And you'll see right now that the form shape is on automatic 0.00. Say that. 0.0088. That's the scale. So it's exaggerated, but if it exaggerated it too much, I mean, it wouldn't even look like the object. Right? And I don't want to see that. Let me just read it. Select user defined. If I pick 1, I mean, I almost have to pick 2. I mean, people hand stuff like this. Maybe that's too much of an exaggeration. Okay, if you were grading that, and somebody was talking seriously about that being a mode, how would you grade it? If you were paying somebody to do this for you, how much would you pay them? much, you fire. Right, that little chit chat, and then if it happens again. Anyway, so we go to edit definition. That's a little bit too unacceptable. Come down here. Automatic 0.0088. If you didn't like that for some reason, say hey, it's kind of hard to see. Then they go to like 0.0. Say 1, 2, a little bit more, 50% more. All right, so it's a little bit more. You can see what's going on. All right, but it still looks like the original structure is just the form. All right, what if I pick 0.000001? All right, then you can't even see the deformation. Right, that's also bad. All right, does that make sense? You guys, just a little common sense. We want to go see it. So that would be this 211 first matched up with measurement from the structure. And I grab that, save it, put it in, and label it as hey, this is the mode that's close with the central frequency. Questions? Look at the second mode. Show, it's kind of tough to see what's going on here. All right, so I'll do the same thing before you know kind of know what's going on at the end of it. Look at that. How would you describe that? That's pure bending as well, but it's in the XZ plane. All right, so a good view for that would be what? The XZ plane.
That's metric.
That top view. All right. Show. Where'd it go? There it is. All right. That's reasonable. All right. Now, somewhere in here, you can also show, instead of colors, you can show the undeflected edges. I'm not sure where you set them. Maybe edit definition or something. If you want to do that, you can. You don't have to. I like to do that. It used to be fine, but all right. So that's a bending mode as well. That's good to ignore. And that's a reasonable scale. Show the third mode. I think that's also bending mode in the XY plane. So I'm just going to look at the front view. There it is. I'll animate that one so you can see it. That's a reasonable scale. That's the bending mode in the XY plane. It's the third mode of vibration for the structure, but it's the second mode. See that? We were trying to stand on that. Now, it's not really vibrating with that magnitude. We're trying to stand on that. Where would it collect?
Like the nodes.
Right? It's just a nodal line. If you go across the top of this, you have a line, but literally a nodal line. I'm going to collect over here too. All right, questions? So here's one that's a little bit more interesting. So that one might be a little bit too much exaggerated, but this is our first twisting proportional mode. Right? We haven't seen this one yet. We've only seen bending mode. This is the twisting mode. And the way you would describe this is not so much about a plane, it's about an axis. So this is the first twisting mode about an axis parallel to the x-axis. Now you know we get some rugged, or rough geometries like the ones you guys have. You can't be able to define it, so that's why I don't ask you. I don't ask you to write it to describe it. Right? But I'm just describing it today because it's for power. Any questions? I'll show you a couple more. There's more bending in that one. That's a bending mode, but it's more of a fleet mode. Because we've got I think it's starting to get difficult to describe. Where would the sand collect? What shape would the sand create?
Across.
Depending on you look at it, a lowercase t across or dash with different lengths. Everybody see that? Wherever it's blue, sand will collect. So sand's going to collect right down the middle here, with left along here, plus with left along here. All right? Any questions? You all see it?
So, one other question.
Go ahead.
So, I think you were saying, 4,800 hertz. So if you got that thing and you excited it,
That's another, yeah, sand collector. Or if I use like a thinner piece of steel, this would bring this down. For instance, that's you can decide that shaker. Let's get on there. Try to change that. So this one's interesting too. This would be best viewed from the top. This is the second mode of bending in the XC plane. Kind of hard to see, but the sand would actually collect at the point. Because there's a nodal point right here. All right, big point, so no less point. The only reason I'm continuing here is I'm trying to get a longitudinal mode, and I think I might finally get it in All right, so you remember the element that we used called the bar element? It predicted longitudinal modes. That's the first mode that type of an element, which we don't even have that option out there. That's the first mode that this would predict. That would predict. You see that that's the longitudinal mode? Anybody? Yeah. So you can see having the animation feature is nice. And this, what we're doing right now is post processing. I haven't really recorded anything in a report, but I'm studying these mode shapes and trying to understand what they're doing. All right. In your case, your structures are, maybe a little bit more involved, and so I'm not really asking you to describe them. I'm just asking you to find the natural frequencies that are closest and computed that are closest to the ones that you measured. So the ones you computed with FEA are closest to the ones that you measured with the modal test, and then do a comparison with the table, and then include the images of the corresponding modes. So let's just say that this is the frequency is really high, let's say this is one of the modes. Then you want to save this image. Everybody know how to do that when you do it? So again, good. Good. All right. You don't need to include this. This is the waste of the paper. This. By the way, election. Scale. You don't really need it. You can see the relative scale. In fact, this is a bit exaggerated. If I was going to submit this, I'd give you full credit for submitting that because I can still just see the basic geometry. But I'd go into the edit definition and bring that out a little bit. Ooh, that's too much. That's a little better. All right, you just want to be able to see it. And honestly, as long as the part still looks like it could be the part, it should be one where it's not. Because I mean, every semester, somebody that makes this thing, it looks like a part. Try that. Yeah, there you go. You don't get credit for that. You're all laughing, but I mean, that, and then they'll get natural frequencies that are zero, and they'll compare them to the measurements. And then percent difference will be in the thousands or higher. And there'll be comments about how good it is, which I'm not even asking for that, right? I'm not asking for your opinion whether it's good or bad, it's just like result. All right. I think hopefully that's the element carried through. There's another one. See, the blue is where the sand was collected into the slime type of circle. All right, so I don't want to belabor the point. You guys have any? I guess we have to show you. Question over here. Good.
Yeah, I do. How did you distort the image using the edit definition?
So go to edit definition on one of the results. Scroll down. Right here to form shapes.
This is the form. Oh, okay.
Usually automatic will do a good job. Right now it's doing a good job. Or you can go and use define. That's even happens to students who use define, but they don't change this one. When that happens, so the story became. So that's you just hit user define. Let's say this is a little too much or a little too less. You pick. Make it a little bit bigger, so 0.007.
0.007.
Yeah, so it's a little bit more.
Okay.
All right. So the other thing I want to show you, I'm going to go on just briefly tonight. So this is what you're expected to do for the project. I'll pull that up. And I just want to show you how you can understand that. All right, so project 2, form solver set to be a model analysis of 2 components of project 1. It should really help out in using answers. Anybody here doing that? I mean, don't ask me questions about it because, like, this looks good because I'll say probably not. But, I mean, I spent a little while to use it. But there are lots of similarities. The big benefit of most other packages is that you have much better selection. So, number 1, I want meshed images of the components. So, one meshed image for each component, which should show the geometry, the element size, factor constraints. If there's any constraints out there, then I know that you did something wrong there on that. So that tells you, look, just looking at the mesh image shows me what you're using. Any questions on that? Number 2, all right, and of course you can treat these separately. So first structure for these 3 things, and then the second structure is table. Number 2 is a table of load testing measured entry frequencies, which for one structure we had 3, the other one we had 2 that we looked at, correct? And the corresponding one element method computed entry frequency. Okay, by corresponding, that's what you have to determine which ones are close enough. Put them in a table with percent difference. And then the third item we need are images of the relevant or corresponding load shapes. So you have 2 more images for one structure and 3 images for the other. 3 more images for the other. A total of 2 tables and 7 images. You with me? Making mistakes? Is that good? Everybody follow that? Any questions at all? Okay, so we're going to go to a new study. And under linear dynamics, click on the linear dynamics and select that, and then it gives you 4 options. First one is the global time history. So what it does is it does time history analysis. In other words, say you can hit the structure with whatever you want. Hit it with an impact or any kind of force that you want to define. You can try any kind of force and motion input. And even where it's constrained, you can define a motion associated with anything that's constrained. It's not really constrained. Zero is constrained. So with modal history, what that is it uses the mold shape results to calculate the response in the linear combination plus the force response. Skip that, we can talk about that. And then maybe this they misnamed it. So there's also frequency response analysis. So you can actually, instead of looking at a time domain response, you can look at frequency. Their choice of titles for these things is off. Like I said, frequencies can really be molded. Mold analysis, that's what it is. But I was going to pick the mold kind of thing to show you something. That's selected. So now we have a new study called dynamic. It's got the same part. Got the same material. Looks like we lost the fixture, that's fine. The only thing I want to do now is I want to go in and edit material. So you still can define your fixtures, you can define the mesh. Look, the extra little feature that's now here. Yeah. All right. So anytime you go beyond a modal with just modal analysis, you're calculating the node shape. You generally want to put in damping. All right. And if we right click on that, as defined, look what happens. You got two options: modal damping, which is what we defined as the first one we defined in the course. We said, hey, no theta 1 low damping ratio for this mode shape, that mode shape, another mode shape from measurement or just from experience. So you literally do that. If you got 15 modes, the default for this, you use 15 modes, you define the damping ratio for all 15 modes. See that? A little weird how to say this. But it's right here. So first mode, last mode, you can define the damping ratios. All right, or you can compute from the material damping. That may be about, you have to find a material that has that included, but it may be possible. The other option, they call it Rayleigh damping, after Lord Strutt Rayleigh, who actually wrote the first book on acoustics and statistics. Volume 1 is pretty much what we know on acoustics, a little bit more, I guess. And then the second volume is everything we know pretty much on usually stuff a long time ago. So I don't think I ever used that language here, but Rayleigh damping is the same. In fact, take a look up here, the stuff that's highlighted in yellow says, as soon as we get Rayleigh damping, the damping matrix is equal to alpha. We use alpha, I think. May write it out, which is the letter times the S matrix plus beta times the K matrix. All right? So you specify alpha and you specify beta. So for example, if you want your damping matrix to be proportional, just the stiffness matrix states or something like that. You just go to 0.1. What happens? Yeah. Yeah, we pick Rayleigh damping, and our damping matrix is equal to 0 times the mass matrix plus 0.1 times the stiffness matrix. Can you tell me anything about the modes? Are they normal? Yeah, proportional damping. They're the same modes that you have. The mode shapes are exactly the same as what you have even without damping, because you have proportional damping. So that's the language we use. We call it proportional damping. That's usually what everybody calls it. Solidworks is calling it Rayleigh damping. Modal damping, you still have the same mode shapes. You introduce modal damping. It's a different way of introducing it. Modal damping is the way that I generally would introduce it. Why do you think that is? Because I can measure things pretty easily. I can make a measurement and get my Z's, my modal damping ratios, and then I can plug it right in. All right. Any questions? So let's go back. Everything's pretty much the same. When you go to result options, this is where it gets a little bit involved because it is calculating your response of each node, which the measure we used before was 10,000, something like that, 50,000, 30,000. It's going to calculate a time response for each node. It's a lot of time response. You have to define the FEA, which is going to do that. So computation, when you speak into even with a recent computer, it's a lot of I tried including that in the project once or twice. I had a lot of students that running the whole weekend with my connection, so I don't do it. And I think something when they put good FEA app on your phone, you got good phone service, right? All right, any questions? You guys clear what to do? Today will be reviewed. Next Tuesday is your exam. All right, first thing for your exam, what are y'all going to do?
Slides.
Look at the slides. Just look at the slides, just in case I throw something in there like, what's the stock grade Stanford?
Yeah.
Right? Validate why I would do something. I tend to look at the slides in the group rather than page. I can talk about the part right now. Let's talk about the middle part. The middle part was multi-predictive system. Application of the second law, everybody's items, application of the second law, writing your equation for motion, everything like this one. I did not a problem. They step over and also proceeding which you couldn't be public. All right, full coordinates. That is control. Vibration control, isolation, absorbers, refrigerants. Things that I thought, like the doctors can't recommend. I honestly thought that stick with me because this is the kind of person I am. I see somebody, I'm looking at that, which is a picture or something on an overhead line that I've seen my whole life. Oh my God, I've seen my whole life. I didn't know they were. And so I wouldn't even probably even look at the slides. But look at your slides, okay? And try to think big picture, little picture, and there's definitely going to be questions on it. That's problems. I try to make it much more manageable, easier, but my idea is using your idea is using it. So look at your slides, look at your homework. Please ask any questions that you have. Right? Don't hesitate. I know you're all bashful. I don't know you're bashful because you're intimidated by me or intimidated by me with the help you. Right? And shoot me an email, ask a question, try to be concise, 100 of you or so, but I'll respond, quickly, or on documents and stuff, image of what you're doing, right? Yep, 20 points. So you could get under 20 points. All right. Originally, I was going to grab some problems from previous tests and throw it for the bonus. And stuff you can't prove that. Basically, everything from last time. Yes. What? Next Tuesday. Today's class. It's project Tuesday. All right. They can do that to you, but the alternative is you can just make project next Tuesday and do final. 24 hours to create it. Right. All right, thank you. Have a good day.
You gonna go to the back or you heading out?